We are pleased to announce a presentation on a study on the design and feasibility of a learning support system using LLM. The Basic Information Technology Engineer examination is the subject matter. The presentation will be delivered by Takumi Mitsuoka, a graduate student at Tokyo University of Science, SUA. We extend our gratitude for your cooperation. First, an exposition of the background and objectives of the research will be provided. In recent years, generative artificial intelligence employing large language model, with ChatGPT serving as a prominent example, has emerged as a significant development. Research endeavors have been undertaken in diverse fields, including research in the domain of learning. Generative AI has been shown to offer numerous advantages, including enhanced efficiency and reduced workload. This section delineates the potential for leveraging generative AI in educational contexts. A significant positive correlation is obtained for the use of generative AI by teachers in the research on the educational use of generative AI. However, the findings also highlight the necessity for pedagogical interventions to facilitate student comprehension and utilization of generative AI. This underscores the imperative for the development of sophisticated generative AI systems that are designed to address the specific needs of students. These findings imply that, in addition to the advantages such as enhancing efficiency and reducing workload in learning, students' utilization of AI must consider the potential for hallucination, defined as the AI's propensity to deceive, along with the management of personal information and copyrights, to ensure sufficient learning outcomes. It is our contention that the absence of consideration for this phenomenon, termed hallucination, may hinder the attainment of optimal learning outcomes. In light of the aforementioned points, the objective of our research endeavors is to develop a learning support system that utilizes LLM, with the aim of assessing the system's efficacy. To this end, we have selected the morning questions of the Japanese certification examination, known as the Basic Information Technology Engineer examination, as the subject matter for our investigation. This report will discuss the feasibility of the system based on 3 results: a proposal of the system configuration, output of answers and explanations using LLM, and automatic classification of questions. In this report, we delineate the LLM utilized in our study. Specifically, we employed GPT 4.0 Turbo, a sophisticated language model developed by OpenAI. This model is an LLM developed by OpenAI, which utilizes data up to December 2023 for training. The parameters were configured with a temperature setting of 0 and the default values established by OpenAI for all other parameters. The rationale behind our selection of this model stems from its status as a multimodal model, equipped with image recognition capabilities and an array of supplementary features. Additionally, its accessibility through the OpenAI API enhances its usability, a factor that was taken into consideration during the selection process. This section delineates one of the techniques outlined in this report, RAG. RAG is a technique that aims to enhance the precision of responses to prompts by leveraging external databases. These databases are meticulously prepared in advance during text generation by LLM, and the technique involves the extraction of analogous data and the utilization of such data. This technique has the potential to yield more reliable outputs and enhance the quality of the results, particularly in terms of reducing the impact of hallucination, when compared to conventional methods. The objective of this report is to construct a system that mitigates the impact of hallucination by leveraging this technique. The subsequent discussion will address the proposed system configuration. The configuration of the overall system is illustrated in Figure 1. The system is designed to fulfill 2 primary functions: the provision of answer explanations and the provision of learning advice. It is hypothesized that system users access the system through the Internet. The system administrator's role encompasses the censorship of products generated by the generation AI and the comprehensive management of the system. In the following section, each function is explicated. Initially, the answer and explanation providing function will be delineated. This function is designed to provide the answers and explanations generated by LLM from the question database. Subsequently, the system administrator is tasked with the meticulous examination of these answers and explanations. This process involves the identification and correction of any inaccuracies, followed by their subsequent storage within the database. In instances where the question has already been registered in the database, it is provided to the user directly from the database. Conversely, if the question is not registered in the database, it is newly generated by referring to similar questions in the database. In the event that the response is determined to be inaccurate, the user is duly notified. At the behest of the user, we are also able to provide similar problems based on the results of the classification that has been completed in advance. In the following section, we proceed to delineate the study advice function. This function is designed to provide users with learning policies and the possibility of passing the exam based on their learning histories associated with their user registrations when they use the system. It should be noted that this function is currently in the conceptual phase, and its implementation is scheduled for a future date. The subsequent discussion will address the database design. The conceptual framework underlying the database design is illustrated in Figure 2. A comprehensive description of each database is provided in the subsequent sections. Initially, the main database is defined as a database associated with each question database according to the year of the examinations. The second database is the question database, which stores the question number, the question text, and the category classification. The categorization of questions is based on three primary types: technology, management, and strategy. The option database contains 4 choices of questions: pre-generated answers, explanations, URLs of image data in case of questions with figures or tables, and more detailed classifications. The more detailed classifications are stored as the results of the major and medium classifications described below. Subsequently, the answer and explanation output is elucidated. The objective of this study is to ascertain the extent to which RAG has enhanced the accuracy of the test. A sample of 50 past questions from the management section of the Basic Information Technology Engineer examination was selected at random for use as the test data. In addition to the 105 aforementioned questions, which differ from the test data, 157 related words in the field of management are stored in the database as data for the use of RAG. The experiment involved the generation of 3 distinct databases: a no-reference database, a database comprising solely words, and a database integrating past questions and words. These databases were then subjected to a comparative analysis to determine the percentage of correct responses. Furthermore, the prompts were provided with the data of the question sentences and the alternatives to generate. The results of the aforementioned answer output are displayed in Table 2. In the absence of RAG, the number of correct answers is 38, the number of incorrect answers is 12, and the percentage of correct answers is 76%. For the word-only database, the number of correct answers is 40, the number of incorrect answers is 10, and the percentage of correct answers is 88%. For the database of past questions and words, the number of correct answers is 49, the number of incorrect answers is 1, and the percentage of correct answers is 98%. In light of these findings, it is conceivable to enhance the precision through the implementation of RAG. It is hypothesized that the observed errors stemmed from the inherent characteristics of the model itself, given their computationally intensive nature. To construct a learning support system, it is imperative to eliminate the influence of such hallucination. To this end, human inspection and correction will be conducted to achieve 100% accuracy. In the following section, the explanatory output will be delineated. The target sample consists of a total of 80 morning questions from the spring semester of 2019. In addition to the question text and answer choices, the correct answer choices were provided as prompts for the generation of explanations. It is important to note that RAG was not employed in the generation of these explanations. The primary rationale for this decision is the difficulty in acquiring data for the database. The most useful data for generating explanations are considered to be explanations of similar problems. However, it is challenging to prepare reliable explanations of similar problems from the viewpoint of cost. Secondly, even in the event that such data were available, a substantial improvement in accuracy would not be anticipated. The results of the commentary generation described below demonstrate sufficient accuracy. For these 2 reasons, we did not use RAG in this study. The results of the explanation generation process are presented in Table 3. The number of correct answers was 76, the number of incorrect answers was 4, and the percentage of correct answers was 95%. These findings indicate that the results were, for the most part, accurate even in the absence of RAG. An analysis of the error patterns revealed 2 distinct categories. Firstly, in instances where the final answers were incorrect despite the provision of correct answer options, a specific error pattern was identified. Secondly, a pattern emerged where the final answers were accurate but the explanations lacked consistency. These observations align with the characteristics of the utilized model, suggesting that these patterns are attributable to its inherent properties. In the context of explanation generation, human inspection and correction will be implemented to attain 100% accuracy. The subsequent step involves the delineation of the problem classification. The primary objective of the classification of the questions is to provide the classification necessary for the provision of similar problems. The classification criteria are derived from the classification system established by the Information Technology Promotion Agency, Japan. The classification process was conducted on a total of 80 morning questions in the spring 2019 semester. The classification process initiates with the segmentation of the inquiries into three distinct categories: technology, management, and strategy. Subsequent to this initial categorization, the questions are then classified into major and medium categories, respectively, according to the results of the classification. It is noteworthy that while the Information Technology Promotion Agency, Japan classification incorporates additional subcategories, many of these subcategories exhibit a higher degree of similarity in content with the medium category, thereby complicating precise classification. To differentiate the questions into technology, management, and strategy categories, RAG was conducted using a database of 300 questions, with 100 questions allocated to each of the three categories of past problems. For the large and medium classification, the syllabus published by the Information Technology Promotion Agency, Japan was used as a database, which is divided into technology, management, and strategy, respectively. First, the results of the three categorizations will be discussed. The results are displayed in Table 4. The technology category exhibited a 92% accuracy rate, with 46 correct answers and 4 incorrect answers, comprising a total of 50 questions. The management category demonstrated a 90% accuracy rate, with 9 correct answers and 1 incorrect answer, resulting in a total of 10 questions. The strategy category achieved an 80% accuracy rate, with 16 correct answers and 4 incorrect answers, resulting in a total of 20 questions. The aggregate accuracy rate was determined to be 88.75%, with a total of 71 correct answers and 9 incorrect answers. The findings indicate that the overall accuracy approaches 90%, while the strategy's accuracy is 80%, which is lower than that of the other categories. The observed discrepancy can be attributed to the classification of strategies and technologies, as illustrated in Table 5. For instance, the strategy encompasses fields related to information systems, yet their contents bear a striking resemblance to those of the technology, resulting in misclassification. The ensuing discussion will focus on the results obtained from the major and medium classifications. Table 6 presents the results for the major categories, while Tables 7, 8, and 9 illustrate the results for each of the subcategories. With regard to the contents of each classification, the questions that were correctly classified in the aforementioned categorization were classified adequately in both the major and intermediate categories. While acknowledging the presence of some bias in each category, we contend that this is attributable to inherent biases in the target problems themselves, rather than any inherent flaw in the classification process. Furthermore, a meticulous examination of the contents of the major and medium classifications generated for the 9 questions that were incorrectly classified in the categorization was conducted. It was determined that the classification was considered correct if the results of the major and intermediate classifications exhibited some degree of consistency with the contents, despite the presence of errors in the categorization. Consequently, we determined that 4 out of 9 questions were classified adequately. To illustrate an instance of accurate classification, consider the following question. In the event of disk failure, following the restoration of data from a tape to disk with a full backup, which method is employed to recover the database by reflecting the updated copies since the time of the full backup from the log? The classification assigned to this question was technology, major category 3, technical elements, medium category 9, databases. Although the assumed classification was management, major 6, service management, subcategory 15, service management, the content of the question pertains to technologies related to databases, and the result of this classification is deemed sufficiently appropriate. Based on these results, the final classification is considered to have an accuracy level of over 90%. The considerations will be discussed in the following section. In this section, the impact of system usage on work reduction will be examined. The process of providing questions to users of conventional learning support systems involves 2 major steps. Initially, answers and explanations are developed for the questions, and subsequently, the questions are entered into the database and made available to the users. In our system, the accuracy of the generation of answers and explanations is over 90% in most cases, and we believe that the system will be effective in reducing the workload in the process of creating answers and explanations to problems. However, it is imperative to address and rectify erroneous answers and explanations, a process that is equally crucial in conventional systems. We anticipate that the implementation of the system will yield substantial benefits, particularly in terms of enhancing the precision and efficacy of the generated content. In light of the aforementioned points, the feasibility of the LLM will be the focal point of this discussion. Initially, it is imperative to acknowledge that the LLM-generated responses, explanations, and question categorizations exhibit a precision rate exceeding 90%. This level of accuracy is deemed sufficient for practical implementation, even in the presence of human verification and correction. It is anticipated that this approach will contribute to a substantial reduction in the workload of system administrators. Furthermore, as this study endeavors to mitigate hallucination by RAG, the system can be readily adapted for other assessments by establishing a dedicated database. It is concluded that the development of a system that can fully benefit from the use of LLM is a realistic objective. It is finally posited that the feasibility of the system has been demonstrated through the proposal of a learning support system configuration that utilizes LLM, the checking of the accuracy of its generation, and the improvement of said generation. Future tasks include the examination of afternoon questions with different question types, the implementation of a learning advice function, the completion of the final system based on the implementation of the learning advice function, the examination of the learning effects of using the system by users, and the improvement of the reproducibility of the generation of LLMs by using other LLMs. This is for reference. Thank you for listening.